Introduction. Father, this park is so beautiful. It has so many swings and rounds to enjoy. My friends also come here daily. I know that. You must like this park. That's why I brought you today here. Thank you, Father. Most welcome, son. Suddenly, earthquake occurs. Are you all right, son? Yes, Father. I'm okay. May I ask you something? Yes, sure. How earthquake occurs? And how can it produce so much destruction? When sliding of the plates occur in the interior of the earth, it causes earthquakes. The shock wave from this sudden movement come to the surface. These waves move along the earth's surface and cause most of the damage. Okay, Father. Now I got the point. And I want to know more about these waves. Okay, son. I will tell you. Children, today we will study more about the wave. Definition. By means of waves, transferring of energy is possible without bulk motion of matter. Wave motion may be defined as a form of disturbance which is due to the repeated periodic vibrations of the particles of the medium about their mean positions, and the motion is handed over from one particle to the other without any net transport of the medium. A stone is dropped in the water. A boy talking with someone. Earthquake are some examples of wave motion. In this chapter, we shall study about mechanical wave motion. Mechanical waves can be produced and propagated only in those material media which possesses elasticity and inertia. These waves are also called elastic waves. Transverse and longitudinal waves. A transverse wave is the wave in which all the medium particles perform simple harmonic motion about their own mean equilibrium position in a direction perpendicular to the direction of wave propagation. Longitudinal wave motion is that wave motion in which the individual particles of the medium execute simple harmonic motion about their mean positions along the direction of propagation of the wave. Transverse and longitudinal waves. Let's make difference between transverse waves and longitudinal waves. Number 1. In transverse waves, the particle of the medium vibrate at the right angles to the direction of propagation of the wave, whereas in longitudinal waves, the particles of the medium vibrate along the direction of propagation of the wave. Number 2. The transverse waves travel in the form of alternate crests and troughs. One crest and one trough constitute one wave, whereas the longitudinal wave travel in the form of alternate compressions. One compression and one rarefaction constitute one wave. Number 3. Transverse wave can be formed in solids and on the surface of liquids only, whereas longitudinal waves can be formed in any medium. Number 4. When transverse waves propagate, there are no pressure changes in the medium, but when longitudinal waves propagate, there are pressure changes in the medium. Number 5. Transverse waves can be directly represented by a sine curve, whereas longitudinal waves can be only indirectly represented by a sine curve. Number 6. Transverse waves can be polarized, whereas longitudinal waves cannot be polarized. Period, frequency, and displacement. Period. The smallest interval of time after which the motion is repeated is called its period. Period is denoted by the symbol t. Its SI unit is second. Frequency. The number of cycles completed in 1 second is called the frequency of oscillation. The reciprocal of t gives the number of repetitions that occur per unit time. It is represented by the symbol V. The relation between V and T is V is equal to 1 by t. The unit of V is per second and is called hertz. Displacement is defined as the change with time of any physical property under consideration. Let's take an example. A block attached to a spring, the other end of which is fixed to a rigid wall. The block moves on frictionless surface. The motion of the block can be described in terms of displacement x from the wall. Displacement relation in a progressive motion. A displacement time function at every instant gives the shape of the wave at that instant. It also describes the motion of the constituent of the medium at that location. A sinusoidal traveling wave is then described by y is equal to a sine kx minus omega t, where y is equal to displacement as a function of position x and time t. A is equal to amplitude of a wave. Omega is equal to angular frequency of the wave. K is equal to angular wave number. Amplitude. A represents the maximum displacement of the constituents of the medium from their equilibrium position. It is called the amplitude of the wave. Wavelength. The minimum distance between 2 points having the same phase is called the wavelength of the wave, usually denoted by lambda. For simplicity, we can say that the wavelength is the distance between two consecutive crests or troughs in a wave. Period. The period of oscillation of the wave is the time it takes for an element to complete one full oscillation. Speed of a traveling wave. A general relation for all progressive waves is given by V is equal to lambda upon t. In the time required for one full oscillation by any constituent of the medium, the wave pattern travels a distance equal to the wavelength of the wave. Speed of a transverse wave on stretched string. Suppose a string is stretched between two rigid supports. If the string is slightly disturbed by plucking, it is observed that a hump travels with a definite velocity along the length of the string. The velocity with which the hump travels depends on the tension and mass per unit length of the string. The velocity with which a disturbance travels on a stretched string is given by C is equal to under root T upon mu, where T is equal to tension in the string. Mu is equal to mass per unit length. Now, a string fixed at one end is stretched by hanging a weight from its other end. The tension in a string is related to the elastic property and inertia of the string. On stretching, the velocity is given by C is equal to under root T upon pi r square rho.
Here,
R is equal to radius of the string. Rho is equal to density of the material. Speed of a longitudinal wave. The velocity of propagation of a longitudinal wave depends on the elasticity and density of the medium. Wave velocity is equal to under root elastic modulus upon density. Principle of superposition of waves. Principle of superposition of waves states that the displacement due to a number of waves acting simultaneously at a point in a medium is the vector sum of the displacement vectors due to each one of them acting separately. Let us take an example. Consider two pulses approaching each other. When the pulses cross each other, they combine to produce a resultant pulse. After crossing each other, they again begin to travel independently as if nothing had happened. This gives rise to the following three important cases of superposition of waves. Number 1. Two waves of the same frequency move with the same velocity in the same direction. This gives rise to the phenomenon of interference of waves. Number 2. Two waves of identical frequencies and amplitudes travel along the same path with the same speeds in the opposite directions. This gives rise to stationary waves. Number 3. Two waves of slightly different frequencies moving with the same velocity in the same direction gives rise to the phenomenon of beat. Reflection of waves. When the wave strikes a rigid boundary, it completely gets reflected. And if the boundary is not rigid, then a part of the incident wave is reflected and a part is transmitted into the second medium. Let us take an example. A pulse traveling along a stretched string and being reflected by the boundary. The reflected wave has the same shape as the incident pulse, but it suffers a phase change of 180 degree on reflection. This is because the boundary is rigid and the disturbance must have zero displacement at all times at the boundary. When there is no boundary, then the reflected wave has the same shape and phase as the incident pulse. Stationary waves. The resultant wave formed by the superposition of two similar progressive waves traveling in opposite direction is called a stationary wave. Antinodes. At some points, the displacement is always maximum compared to other points. These points vibrate with maximum amplitude and are called antinodes. The separation between successive antinodes is lambda by 2. Nodes. At some points, the displacement is always zero. These points, which are always stationary, are called nodes. The separation between successive nodes is lambda by 2. It is observed that the separation between a node and adjoining antinode is lambda by 4. Summary. Let us summarize what we have learnt. Wave motion may be defined as a form of disturbance which is due to the repeated periodic vibrations of the particles of the medium about their mean positions. In transverse wave, all the medium particles perform simple harmonic motion about their own mean equilibrium position in a direction perpendicular to the direction of wave propagation. In longitudinal wave, the individual particles of the medium execute simple harmonic motion about their mean positions along the direction of propagation of the wave. The minimum distance between 2 points having the same phase is called the wavelength of the wave. The velocity of propagation of a longitudinal wave depends on the elasticity and density of the medium. The displacement due to a number of waves acting simultaneously at a point in a medium is the vector sum of the displacement vectors due to each one of them acting separately. The resultant wave formed by the superposition of two similar progressive waves traveling in opposite directions is called a stationary waves.